Hello, in the last video we ended up just by highlighting this expression for the interaction part of the Hamiltonian, or the part that contains the perturbation, and now it becomes important to evaluate the second order approximation to an eigenstate in the interaction picture. This is to continue with our lecture on linear response. Now, the first thing we need to do, let's do this rather quick, so then we of course remember that we have a Hamiltonian of the form H0 plus W of t, where W of t is the perturbation, and then this perturbation in the interaction picture, we said that it was given by e to the I over h bar h0 t w of t, which is in the Heisenberg picture, times e to the minus I over h bar h0 t. Now, the second order correction of a state vector in the interaction representation, we can see that it reads in the following way. So phi of t, I'm skipping a big let's say thing here, but you will see in the next video where this second approximation came from. For the meantime, just believe me please. So minus 1 plus 1 over I h bar integral from 0 to t w of I of t dt plus 1 over I over h bar square, therefore minus infinity to t. This is d tau prime, and this is from minus infinity to tau prime of d tau. Let's scroll over a little bit. This is times wi of tau wi of tau prime, all of it acting on phi of minus infinity. Okay, so this is, let's say, the constructed second order state. We will see in the next video where this second order state comes from. If you want to, let me rewrite it downstairs to see if we can look at it in a more compact way. So 1 over I h bar integral from 0 to t, perturbation in the interaction picture, sorry, this is in tau, d tau plus 1 over I h bar square integral from 0, now this is minus infinity here in the integrals, sorry, minus infinity, this is 2t of d tau prime from minus infinity to tau prime of d tau, perturbation evaluated in tau, perturbation evaluated in tau prime, okay, all of it acting on phi of minus infinity. Okay, now this is the second order approximation, and so what we want to do here, just in advance, I want to tell you, is to express to any order n the approximation for the eigenstate in terms of the time ordering operator of the product of perturbations. Okay, this is what we want to do, and now we want to do it for second order, so just up to two products of the perturbations evaluated at two different times. So to do this, now we're going to consider the second part, or the third term of this second order approximation, which is this. Okay, and from here what we're going to do is that we're going to consider just this integral we're going to rewrite this integral. We're going to change some times here. So then the integral from minus infinity to t of dt prime from minus infinity to tau prime of d tau of wi of tau wi of tau prime. Okay, so this integral has an identical value to the following integral, to the integral from minus infinity to t of d tau, integral from minus infinity to tau of dt prime, wi of tau prime, wi of tau, where what I just did was just switch tau and tau prime. Okay, these two integrals give exactly the same number. So these integrals are numbers, and they are the same number. Now, the problem here, there's a small problem. The order of the product wi tau and wi tau prime was inverted here. So this is inverted order. Okay, so then what do we want to do here? Since these two generally don't commute, therefore both of these above integrals must be written in terms of the time order operator as follows. Okay, so then now we're going to introduce for these two integrals the time order operator, and then we're going to start with the first integral in blue. Okay, we're going to write integral from minus infinity to t of d tau prime, integral from minus infinity to tau prime of d tau, wi of tau, wi of tau prime. Okay, this is equal to the integral from minus infinity to t of d tau prime minus infinity to tau prime of d tau time order of wi of tau, wi of tau prime. So then this time order operator just puts to the right the operator that is evaluated at the smaller time, and to the left the operator that is evaluated at the later time. So to the right the earliest time, and to the left the later time. Okay, so then that's for the first integral that we have here. So for this integral, now we're going to do it for this integral. Okay, and then we're going to do it in purple to not just get confused with so many integrals. Minus infinity to t of d tau, minus infinity to tau of d tau prime, wi of tau prime, wi of tau. Okay, and this is nothing but minus infinity to d tau to t minus infinity of d d tau prime to tau time order. It will be the same time order because this will just arrange the product according to the position of times in the timeline. So then we can just write the same product as we have here with no problem. And just a quick reminder that when I have two operators, a of t and b of t prime, and I apply the time ordering operator to the product of these two operators, the way to actually expand this is like this: a of t, b of t prime. This is equal to this product when t prime is less than t. So that means that we just write t of t minus t prime. And when t prime is greater than t, then the product is b of t prime, a of t. So that means that you have to put to the right side theta of t minus t prime minus t. So then when one time is greater than the other one of these two terms will survive. Okay, that's how we interpret the time ordering operator in products of operators evaluated at different times. Now, so what's next here? So what's next here is that we're going to add these two integrals. So to the left side, these two integrals have the same value. Okay, so this integral here gives exactly the same value as this integral here, so what we're going to do is that we're just going to take twice 2 times this integral. Okay, so then that means that 2 times the integral from minus infinity to t of dt prime, the integral from minus infinity to tau prime of d tau of wi of tau prime is equal to what? So then we just go back here to these integrals that contain the time ordering operator, and then I add these two integrals. They have the same argument inside, but they have different limits. So when we add integrals, we add the limits as well. So what we're going to do is this. Let's look at the limits of d tau prime here. So d tau prime here go from minus infinity to tau, and here they go from minus infinity to t. And tau, since it's the integration variable, is supposed to be between minus infinity and t. That means that if we add the regions of integration, the new integral in d tau prime will go from minus infinity to t, and the new integral in d tau will go as well from minus infinity to t. Okay, so then what we have here is that this integral, after we have added the regions of integration, goes from minus infinity to t in d tau, and goes from minus infinity to t in d tau prime. Okay, and what we're integrating here is the time order product of the perturbations evaluated in tau and in tau prime. Okay, so finally we arrived at the following formula. The integral from minus infinity to t of d tau prime, the integral from minus infinity to tau prime of d tau of wi of tau prime is equal to 1/2 the integral from minus infinity to t of d tau integral from minus infinity to t of d tau prime, when it's integrating the time order product of wi of tau prime. Okay, so this is the formula that we actually need. This formula we will need to do what? To come into the second order approximation that we have here and replace it here. So now we don't want this, but we want the new formula where we're always integrated after t. Okay, so then that means that my new state, the new second order approximation of state phi of t is equal to 1 plus 1 over I h bar integral from minus infinity to t of d tau wi of tau plus 1 over 2 I h bar square integral from minus infinity to t of d tau integral from minus infinity to t of d tau prime time order of w sub I of tau prime. We close here this and we close here this, and all of this acting on phi of minus infinity. So then this is the actual approximation that one usually uses when uses second order corrections in the state. And again, let me write it in a more compact way here downstairs. Always it doesn't fit. This is, I write too big and the space is too short, so it goes both ways. So then 1 plus 1 over IH bar, integral from minus infinity to t of the tau w sub I of tau plus 1 over 2 IH bar square minus infinity to t of d tau minus infinity to t of d tau prime time order of w sub I of tau w sub I of tau prime, close here, and this acting on phi of minus infinity. Okay, and then so this is the second order correction to quantum state psi of t in the interaction picture. Okay, in the interaction picture we will now see where this formula came from in the next video. And even though we're only using this to linear order, that means we're only using this to first approximation, it is useful to actually know how to construct this, and that we can do this for any arbitrary order and express the corrections in terms of integrals of the time order products of the perturbations evaluated at different times. So this is all, and see you in the next video.